Cord, how are you doing this morning?
Good morning. Well, thank you. How about yourself?
Doing pretty good. You ready to jump into our last lecture of this class?
Sounds good to me. I still haven't done anything about it though.
Well, this one, honestly, if you remember your steady state sinusoidal circuit analysis, that's all you're going to need. So you could
Sounds good to me.
technically solve this problem with a circuits 1 level of expertise.
Cool. Well, I'll let you know if I can.
Okay. We're going to look at a circuit, and it is going to be an unbalanced three-phase circuit. And so the circuit in question here, give me a moment to draw things out. Let's see. So we have a delta connected three-phase source. We're going to have some transmission lines here, which I will call Z wire, connecting us to our load. And lastly, we are going to have a delta connected load. And this delta connected load is going to be unbalanced. So I'm going to call this guy Z delta A. This guy here, Z delta B. And lastly, up here, we will have Z delta C. And, excuse me, let's start defining a few things. So let's say that our voltage, source voltage VAB is 416 angle positive 60 degrees volts RMS. And if we have a positive phase sequence, we'll be able to use that information to figure out VBC and VCA. So we'll get to that in a moment. Our transmission line impedance Z wire is going to be simply 2 plus J1, and our transmission lines form a balanced network, so they all have the exact same impedance. And then finally, we'll have Z delta A is 4 plus J6. Z delta B will be 10 plus J4. And lastly, Z delta C will be 20 plus J8. So this is an unbalanced network because our load impedances are not the same per phase. So what that means is that a lot of the relationships that we have exploited, specifically the instances where we could say that our line currents at our line currents through our transmission lines were balanced, meaning that they all had the same magnitude and were separated in phase by 120 degrees. We can no longer guarantee that to be true. Similarly, our phase currents through our load should also no longer have the same magnitude and be separated by 120 degrees. And we should see then that our line voltages and phase voltages at the load should also not be equal in magnitude and separated by 120 degrees. So we're not going to be able to rely on all of our tips and tricks that allowed us to simplify our circuit analysis. So effectively, we cannot develop a single phase equivalent circuit for this system because it's no longer balanced. So we are going to have to rely on tried and true circuit analysis techniques to solve this guy. So let's talk specifically about what quantities I want to solve for, because that would influence our analysis. So I want to know what our line currents are. Yeah, I think that'll be enough. We could, if we were so inclined, figure out how to do phase currents and all that kind of good stuff too, but let's just leave it with something simple for right now. So, chord. If I wanted to figure out 3 currents in this circuit, what circuit analysis technique do you think I should probably give a go?
Mesh.
Yeah, exactly. It's that simple. So instead of worrying about all these crazy three-phase relationships, we're just going to use mesh and nodal to get the information that we want. So I'm going to call this guy mesh 1. This guy mesh 2. This guy mesh 3. And this guy mesh 4. And as it turns out, we're not actually going to see a whole heck of a lot of mesh 1 in our circuit analysis. And so what I mean by that specifically is if we were to do Kirchhoff's current law, or excuse me, Kirchhoff's voltage law around mesh 1, because our source is balanced, we would find that we're just going to have the sum of the voltages is equal to 0, which doesn't really help things out a lot. So it may be in our best interests to develop a slightly different relationship here. But let's see if we can get enough information just using these relationships, right? Because our phase current I1 isn't going to be 0, but we may need to, and we wouldn't necessarily need that to figure out. Yeah, anyway, I'm kind of floundering, but we'll go with it. All right, so circling back around to our source voltages, because our source is balanced, and I've said it's a positive phase sequence, we could say that VBC, we're going to shift it by negative 120 degrees, so that's going to be minus 60. And VCA lags VBC by 120 degrees, so that's going to make this minus 180. And so now we can simply get around to writing equations. So we can start with KVL at mesh 2. We would see negative VAB, which we know, plus I2. Oh, and I guess I should go ahead and label all of these are RMS phasor currents times our impedance ZW plus we're going to have I2 minus I4 times Z delta A plus I2 minus I3, sorry, times ZW is equal to 0. So there's no controlling values or anything like that. So we just have an equation right now, a single equation with 3 unknowns, our mesh current I2, I3, and I4. So everything seems hunky-dory thus far. Okay. So now we could do KVL at mesh 3. Where we would see negative VBC first, plus I3 minus I2 times ZW, plus I3 minus I4 times Z delta B, plus I3 times ZW is equal to 0. So we just followed our mesh current 3 around and took care of everything. And then lastly, KVL at mesh 4, starting at the bottom left-hand corner, we're going to see I4 minus I3 and Z delta B plus, it's going to be I4 minus I2 Z delta A plus I4 and Z delta C is equal to 0. So we have 3 equations and 3 unknowns. And because they're dealing with complex numbers, we should have to throw this stuff into MathCAD. So let's go ahead and do that and make sure that we have enough information to solve this thing. And if not, we'll talk about where we can get some extra equations. Taking a minute to open up the MathCAD. There we go. All right. So I'm just going to define some variables first so that I can be kind of lazy. So VAB was 416 angle negative 60 degrees volts. VBC was 416 angle, sorry, this first one was positive 60 degrees, wasn't it? we had ZW was 2 plus J1. Actually, I need to do it as 1J or it'll freak out. And let's use some units. And then we had Z. And to save myself some trouble of having, actually, yeah, I'm just going to call it ZA then, because it doesn't like when I put a Greek letter and then another letter after it. So ZA was 4 plus 6J ohms. ZB was 10 plus J4. And lastly, ZC is 20 plus 8J ohms. So now I'm going to throw things into a solve block where I'm going to have my 3 mesh currents. So I'm going to say I1, gas value of 0 amps. I2, let's do 1 amp actually, because sometimes 0 leads to errors. And then I have my equations. So I believe it was negative V AB plus, let's see, I2 times ZW plus I2 minus I4 times ZA. And let me know if I'm making any errors in my equations here, please. And then I2 minus I3 times ZW is equal to 0. So I believe that's my first equation. Let me just peek over at it. I2 minus I4, I2 minus I3. I2 minus, yep, okay. Then we had negative VBC plus I3 minus I2 multiplied by ZW plus I3 minus I4 multiplied by ZB plus I3 multiplied by ZW. 0. And then lastly, we had I4 minus I3 times ZB plus I4 minus I2 times ZA plus I4 times ZC equal to 0. Do all of those equations look correct?
Yes, sir.
Cool deal. All right, so now what I like to do in case I need to manipulate things is I throw my answers into a matrix. Excuse me. I got 2, 1. Oh, what am I doing? I2, I3, and I4. Those are my variables. Oh, dang it. Okay. So this needs to be 2. This needs to be 3. This needs to be 4. All right. All right. So we got answers. So those answers are in rectangular form. Nothing wrong with that, but I prefer to have my answers in polar form for voltages and current. So I can change that by going to math formatting. And there we go. So 44.597, let's cycle back to the, can you see the engineering pad thing? Or do you see the math CAD?
Just the math CAD for me.
Okay. Reorganize everything so I can that. So solving. So I1 was 44.579. Angle of 1.578 degrees. Amps RMS. I2 was 34.870 degrees, or 34.870, with an angle of negative 59.639. And lastly, I3 was 12.2, angle of negative 22.775 degrees. Oh, excuse me. All right, so if we look back here, how can we express our line currents in terms of our mesh currents?
Add or subtract them as necessary to get the correct current.
Right. So, for instance, the line current IAA would be what combination of mesh currents?
Should just be I2.
Yeah. Oh, and I didn't explicitly write these directions here, so let me go ahead and do that. Didn't notice it. Yeah, you're right. You're absolutely right. So IAA is simply I2.
I believe the I2, I3, and I1 answers should all actually be I2, I3, I4.
You are absolutely correct. I keep getting myself mixed up. Thank you. So that's 44.579, angle 1.578 degrees, amps. All right, so IBB. What would that one be?
It'll be I3 minus I2.
Okay. Let me grab my calculator real quick. So I3 minus I2 gives me 41.307, angle of negative 130.702 degrees amps RMS, and we can definitely see now that our line currents are not balanced because they have different magnitudes, and also the separation between these first two angles is definitely not simply 120 degrees. Lastly, we have our line current ICC, which I believe is just going to be negative I3. So that is going to give us 34.870 angle positive 120.361 degrees amps RMS. So figuring out the line currents was fairly straightforward. Figuring out, let's see, our phase currents, and we're not going to go through the math here, but I just want to make sure that we could figure things out. So if we wanted to figure out this phase current IAB, what would we do?
Should just be I2 minus I4.
Right, and then similarly, this phase current IBC would be I3 minus I4, and this phase current ICA would be negative I4. And then from all of those, we could easily get the voltage drops, our line and phase voltages, because they're the same thing for a delta connected load, could be gotten using Ohm's law. Let's see. So the only question that the only current that I'm really uncertain about, so for instance, I could get this phase current or the phase currents through the source. How could I go about figuring those guys out?
You'd have to find I1 most likely.
Well, you would have to find I1. However, there are some relationships that I believe that we could and should exploit. So let's start with something pretty straightforward, though. Is there a loop that we could use that would enable us to find I1 directly? Because that would make things pretty darn simple.
Yeah, just use mesh 1.
So if we do mesh 1, we would have VCA plus VAB plus VBC is equal to 0. The current I1 doesn't show up anywhere because the voltage drop over those voltage sources isn't dependent on the current I1. Does that make sense?
Yes, sir.
So we're going to have to effectively come up with a different, I don't want to call it a mesh to use because it's not a loop that doesn't contain any smaller loops, but we're going to have to come up with another loop. And so a particularly easy one, I think, would be if we followed the current around the outside. All right. If we followed this path, we would have VCA plus mesh current I2 times ZW plus mesh current I4 times Z delta C plus mesh current I3 times ZW is equal to 0. And well, shit, that still doesn't let us get I1, does it? That's just another uglier equation. All right.
But that should give you ICA, right? No, excuse me, sorry, the freaking left-hand ICA.
So that equation would be entirely based on mesh currents I2, 3, and 4. So it wouldn't give you ICA for the same reason, because that current ICA is flowing through the voltage source. So here's what I posit, okay? So that was maybe not the best idea, but that's all right. Oops, I didn't mean to erase that in there. So our voltage source is balanced, which means the currents that are so if the voltages are balanced, does that mean that the currents are also balanced? I would think so, but I'm not 100% sure on that. So what I was thinking about was applying Kirchhoff's current law. So for instance, if we applied Kirchhoff's current law at this node, we have this current flowing in, which is ICA, this current flowing out, which is IAA that we know, and this current flowing out, which is IAB. If our source currents are balanced, then that means that IAA, let me rewrite that so it doesn't look like such chicken scratch. Would be equal to ICA minus IAB, where we know that ICA is simply IAB times 1 angle minus 240 degrees minus IAB times 1 angle 0 degrees. And that would allow us to solve for IAB, and then once we knew IAB, we could get IBC and ICA. So that's what I'm gonna go with. We're gonna make an assumption here that I believe is correct, and I'll have to look into this just to make sure. I could do it with a circuit simulation. That since our voltages at our source are balanced, the currents flowing through our source should be balanced as well. But I'll have to double check that. So this is a maybe. And I will make sure to not ask you guys to do something like that, because if I can't do it, then there's no expectation that you should be able to do it either on your exam or anything. So I'll make sure that it's something that you could get using simple circuit analysis techniques. I guess another way to approach this guy could have been, let's see, if we did nodal analysis, then we would just have a whole bunch of supernodes. Yeah, I'll have to look at that. So the source currents, that's a question mark right now, but all of the line currents and then, excuse me, and all of the load-based quantities, I'm sure are correct. Excuse me. Alrighty, so hopefully that wasn't too confusing. Things kind of ran off the rails at the end there. But for the most part, we can analyze any unbalanced three-phase circuit just by employing our basic circuit analysis techniques like nodal analysis, mesh analysis, Ohm's law, KCL, and KBL. Alrighty. Do you have any questions or anything, Cord?
None that I can think of.
Alrighty. Well, hopefully things didn't get too confusing at the end there when I made an assumption that I'm not 100% sure is valid. So I'm kind of pissed off that I can't think my way through this right now, but oh well. I'm sure
That's math.
Yeah, I'm sure I'll figure it out 5 minutes after this closes and then have to make another short video and be like, aha, I did it right, or oh shit, I did it wrong. So anyway, all right, well, if you don't have any questions, then that's the last lecture for Circuits 3. I'm going to post the exam to open up on Monday. I know that the quarter technically ends on Thursday, and I'm not saying this to you because you have extenuating circumstances. Because of your military training and all that kind of stuff. But for all the other students, I believe that grades are due, since none of you guys are graduating, grades are going to be due the following week. So I believe I can still offer you a full week to turn in the test, despite the fact that the circuit, the quarter technically ends on Thursday evening. I'm not saying you have to use the full week by any stretch of the imagination. So if you want to turn things in early, by all means do so. I'm just saying I am allowing you the full week that I've done on all the previous tests. All right, so catch you guys later. Have a good rest of your day, Cord.
Thanks, sir. You too.